and also read the program. So in your last obstacle before actually going on holidays after the summer. So we try to make this as enjoyable as possible. Feel free to interrupt me after the question if you want. And the subject today is to tell you a little bit more about an initiative which is called Software Heritage, which is something that was started a few years ago. And we are focusing on software in general. But maybe a few words of introduction. I'm a computer scientist. I have spent over 30 years doing teaching and research. I spent a quarter of a century in everything related to open source, open access, open science in general. And then when you grow older, you have a beard. I no longer have hair, but that's another story. It was much older than that. I decided to start and try to help building infrastructure for the common good. There are many. The one that I talked to you today about is Software Heritage, but I'm also member of the National Committee for Open Science in France, in the Ministry of Research in France. And we go over all this. So it is a landscape. Okay? You are all here for programming language schools, and of course you know the software is changing the world. The software doesn't come out of the blue. It is written by human beings in the form of source code. And actually, you will see how old I am. I mean, this book by Howard Wilson, who is an MIT professor, who contributed to Creative Commons, contributed to the semantics of programming language, contributed to the Free Software Foundation, contributed to the creation of Scratch, which is used to teach early programming to kids. In his book, both the programs must be written for people to read and only accessorily for machines to execute. Now, we are in 1985, this is an MIT professor, so you can feel this is kind of a joke. He's telling students, if you turn in homeworks I cannot read, you will get the bad grade, okay? But actually it is deeper than that. Today we have access to an incredible amount of source code which is available, and this message becomes a little bit clearer. For example, these are a few lines extracted from the 60,000 lines of assembly code that were on board the lunar landing module when in summer 1969, mankind managed to put a man on the moon, thanks to a woman, Margaret Hamilton, to actually led the team of developers. If you look at this picture, this code here on the left, you see the assembly code. And if you still know what assembly code is, because you are no longer used to do this kind of thing, it's fascinating the way you are programming back then. But the part on the right, these are comments written in plain English, telling the story of what the software is meant to be doing. Let me take a couple of seconds to explain what is happening here. These are the bunch of lines of code which are run when the lunar landing module is approaching the surface of the moon. I don't know if you remember this picture, because the NASA actually put out a very nice movie a few years ago with renewed reels. You see there is this triangular window, and you see the surface of the moon coming in. But if you continue like that, you just crash. You need to turn around the lunar landing module, fire up the rocket to slow down this. This is a code telling the astronaut to turn the silly thing around, okay? To turn around the lunar landing module. How does it work? They just check whether the landing radar, LR, there is a landing radar, is already in the right position, because you send a radar signal to the surface. If the radar signal comes back, it means it is in the right position, you already turned the landing radar. If it is not the case, you tell the astronaut to do the operation, and if the astronaut says, yes, I did it, well, basically, already in 1960s, they knew that the biggest source of error lies between the keyboard and the seat. Okay, so they will say, let's check whether the astronaut did it. So you jump back to check the landing radar, antenna position, you keep plugging the astronaut to this system. So even if you know nothing about the assembly code, this text is very easy to read later on. So the comments go to the humans, not to the machine. Now you may say, well, that was assembly code. Right? Of course, we put comments. But we no longer put comments in modern programs because the high-level programming languages are self-explanatory. Let me disagree with that point of view right away. But fast forward a little bit. This is an excerpt of COVID scene, which was actually COVID simulator developed at UCL in the UK to monitor the evolution of the COVID pandemic. You will see this is written in a more high-level programming language, much more modern, and yet you still have tons of comments around, comments which are designed for the humans, not for the machines. So to sum it up, President Schuster, who was the board director of the Computer History Museum, a beautiful institution which is not too far south from here, wrote in a beautiful paper in 2006, having access to the source code program provides us with a view in the mind of the designer. That's the reason why we need to care about source code and not just for the binaries that we actually execute. Now, software has exploded thanks to the open source, free software open source movement. The amount of software is mind-boggling today. And actually today we tend to forget, not you, I mean we are in the same boat here, but a lot of people outside tend to forget that software is just not a tool, not just a tool, but actually it is really a concentrate of knowledge. It's a special form of knowledge because it is a human, readable, executable knowledge. It can do it, I say. And today, for example, you know, after during the epidemic, you had this nice article. I don't remember, it was in New York Times or it was Washington Post. A column by Yuval Harari saying that the real antidote to epidemic, replaced by any challenge for mankind, is not by closing borders and focusing on yourself, but actually by creating collaboration and scientific knowledge in a collaborative way. Okay, so to show this concretely, I mean, software today powers all of modern research. And actually, this was a mantra we were saying a lot of times. Software is not just for computer scientists, software is designed to use in all kinds of disciplines of research, but we didn't have hard numbers. Now, 3 years ago, the Ministry of Research in France decided to build what we call the French Open Science Monitor. This is a tool which is used by our, let's say, policymaker to track the evolution of the open science policy in France. And one of the facets of this monitor is to check how many articles, research articles in different domains and fields actually use, create, and or share software. Here you have the hard numbers, and you will see that even in humanities, social sciences, psychology, etc., everybody is using software. Actually, most of the software written is not by us in computer science, but by people in other fields. Guess where? Life sciences. It is the most productive area today. And as Donald Clark, which is a mythical person in the history of computer science, wrote a few years ago in a nice article, he also said, you see, software is knowledge. It's important to keep it. It's important to explain it. But if you really want people to listen to you, you need to tell stories. There is no better way of teaching than by telling the story behind the software or the research areas that we are working on. And he was advocating for actually writing the stories of the software that are changing the world. But even having said all that, the state of the art today is really not good. I mean, if you look, for example, in academia today, we, even us, I mean, in computer science and software engineering, we should be the experts, okay, on writing software the right way. We face tons of issues related to reproducibility, lack of access to the source code, and lack of documentation how to use it, lack of information how to build it in a proper way. And I don't know if you are involved. Let me check. Any of you heard about or is involved directly in artifact evaluation committee? 1, 2. Not enough, come on. I mean, you know, what happens is that in the best conferences, even programming languages today, like Popper, Leaks, etc., we usually ask, in these days, people that present an article containing information on a new static analyzer or a new result here and there, to make accessible the software that has been developed to obtain that result. And there is a special committee that is separated from the program committee. It is called the Artifact Evaluation Committee. Usually, we try to get on board early researchers or PhD students to come read the paper and then check whether the software associated with the paper, one, if it exists, okay, if you can get a hold of it, then if you can compile it, and if you can run it, and whether it actually does what it is supposed to do after what you expect from the paper. Well, the situation is, today is a real disaster, I have to say, unfortunately. So, everything blue in these slides are pointers. So when you get a copy of the slides, you will get a copy of the slide, you can click there, you can get the arguments substantiated and same. So in academia, we are not managing our software well. And in industry, come on, it's a major disaster too. Okay? Cyber security issues, security analysis, cost, quality of the software that is distributed, etc., etc. It's really complicated. So if you want to tackle all of the areas that I mentioned above, so respecting software, make it visible, make it reproducible, make it better as quality, we need a dedicated infrastructure for handling all this. So here is where we are going to need our effort to build this kind of dedicated infrastructure. The code name is Software Heritage, because at the beginning we're thinking of the name, and so software is our heritage because it contains a significant part of our cultural heritage. This is the name. But in a nutshell, the mission is to go out, fetch and collect every single line of source code ever written, which is publicly available, bring it in a single infrastructure, preserve over time, and make it easy accessible to improve the quality of software for the future. So you can think of it as a reference catalog, so no matter where software is developed, most of you are using GitHub today, but a lot of people using other platforms, IPI, NPM, whatever. It is an archive, because software is fragile, actually. I don't know, you are much younger than me, but if you remember, in 2015, Google Code was shut down, 700,000 projects unplugged. GitHub was acquired by the rival competitor GitLab and closed down in 3 weeks, 130,000 projects unplugged. And 4 years ago, Bitbucket, another platform, removed support for Mercurial as a version control system, 350,000 projects unplugged. Okay, so no, putting your software on a co-hosting platform, be it GitHub or something else, that is not the way you should maintain the reliability of your software over time, because these are co-hosting platforms, not archives. We are building an archive. The last but not least, and probably most interesting for you, what we try to build is a real research infrastructure, I mean, a sort of very large telescope that allows us, that allow you, we hope, to do massive analysis of the galaxy of software development today. Actually, as a little personal anecdote, my best friend, one of my best friends is another Italian, but he moved to Baltimore 30 years ago. He spends 30 years of his life to coordinate as mission head of the James Webb Space Telescope. Okay, so that is a 30-year, $10 billion initiative to build a beautiful tool that allows us to explore the origin of the universe. I have always been extremely admirative of our colleagues in astrophysics that managed to bring together the full astrophysics community to fund such a thing. And I have to say, we need to learn from them and build a similar infrastructure for doing the same for software that has direct impact in our society every single day. Okay, so what we try to do is the initial building block of this infrastructure. So how do you build something like this? I know we are not very far from Silicon Valley, but no, we didn't want to go and look for venture capital in a company, because after seeing Google, that is not lacking any money, shutting down Google Code, another company buying and selling and closing up infrastructure, it was clear we had to follow something else. So we decided to go for a long-term, non-profit, multi-stakeholder initiative to build one infrastructure with a clear, simple mission. You know, the Unix mantra was always to be do one thing well and interface with the other. So the one thing we want to do well is to collect the server share, but then interface with application in cultural heritage, industry, research, etc. This was supported at the beginning by INRIA, which is my host institution today. We had a collaboration agreement with UNESCO in 2017, and we actually have the largest archive of software source code ever built. This is over 385 million. The picture here is not up to date, I do not change the number every time I give a talk, but if you go in the archive, you will see almost 400 million projects, more than 25 billion unique source code files, more than 5 billion unique commits. And how is it supported? This is supported by a bunch of different stakeholders. It runs from companies to government agencies, to academia, to institutions. And by the way, there is a lot of white space, so if you know somebody that wants to join, let them know that we are very open to support. Now, this is a picture actually taken from this archive. You see, this is a long queue of platforms where you can find software today. The biggest fish in the pond is GitHub. Right? GitHub has over 350 million public projects today. Then you have GitHub.com, 5 million projects. Then you have Bitbucket, something like 3 to 4 million projects. But then you have a very long queue. Actually, we are archiving more than 5,000 different code hosting and distribution platforms every day. There is a long queue where you find more than 2 million projects that are only present on this little thing. You know, as you know very well, usually quantity and quality are not the same thing. So it doesn't mean that you have millions of projects that the only interesting things are there. Usually the interesting things are on the other part. And how do we do this? Well, under the hood, in over 10 years, we built a giant crawler that connects to all these different platforms. If you are familiar with the Internet Archive, you can think of what we do as something like the Internet Archive, but for code. The big difference is that archiving the web is kind of easy technically because there is one standard, HTTP for connection, and one link for tracing pages which are URLs. Now, since we are computer scientists and computer technology, we love to invent new things. Okay, so every single one of these platforms has a different feed, a different API, a different language for interfacing with them. So we have to build tons of adapters. And this allows us to get a list of the 380 million projects. And then, so you see, it's kind of a bubble tower. You need to build a lot of adapters for these languages of this platform. And since you go to the first floor of the bubble tower, then you discover there is another floor because the people is using tons of different tools to keep the version control of the system. Git is very popular today, but you find a lot of Subversion, Mercurial, Bazaar, etc. Darts, if you want exotic version control system. And then package manager, tons of package managers. IPI has a form, Debian has another, Fedora has a third, etc. So what do? Well, we decided to go the extra mile and actually build, analyzer, and converter for each of these version control systems and put everything, they build the whole history of software development into a single giant direct acyclic graph, which is very simple. If you look at the object directory in the graph, there are the file contents, the directory, the revision, the snapshot, and the origins. Each of these objects is identified by a single cryptographic signature. So if you are familiar with the Git model, this is kind of a Git at the scale of the time. And this contains the full history of software development over 70 years in a single graph that contains 50 billion nodes, 800 billion edges.
So how easy is this to compress? Because basically I'm guessing that since you are keeping all this historical data, it won't go stale because it's historical. So does that let you do a lot of compression?
Very good question. Look, if you don't mind, I will answer it later because I have a slide on this. That's a very good question, absolutely. So we keep all the versions, and very good point. But the interesting point here, you see, when we took this decision, that was 10 years ago, is that having this particular data structure, which is dedicated, already enable us to do some kind of compression, because the same file, if it appears in 1,000 projects, it was stored only once. And you know how you are developing software today. Everybody does a fork. So basically, you want to add a comma on a header inside the Linux kernel. First thing you do a fork, which is technically a full copy of 100,000 source codes. Then you change it, a comma, and then you send what is called a pull request or a merge request. So you send a message to the owner of the original record saying, do you like my little change? Please come and fetch it. Very nice, but now you have thousands of copies of the Linux kernel around the world. If we didn't use this data structure, we would be dead, okay? But now who cares? I mean, it's just a duplicated graph. So you made another copy, you can add the link from origin to the same snapshot of the record. So nothing really rocket science, but you will not believe how many people don't get this very easy point when you talk about archiving software.
The build environments are necessary for like compiling verify?
They are a very good point. No, we do not preserve the building environment because we really focused on the only thing that 10 years ago we saw nobody was caring about, which is the source code. Well, you had people working on that, virtual machine, Docker images, etc., etc. But even here, wait a second, you will see we still trying to do something in that space. So, how are the identifier built? Again, if you know already about Git, you can read your email for 2 minutes. Okay? If you don't know exactly how Git works, that's the idea. So the identifier that we build contains a hash of a file, for example, or then a tag that says this hash is for a content or a directory, etc. A schema version, because the hash may need to be updated. And the particularity of hash function is that the input space is much bigger than the output space, so we eventually, every hash function will have collision, okay? So eventually we need to update it. So version 1 for the moment stay there, and this graphics that says this is not any hash, it is a hash for software. And the tags can be the content, the delete, the directory, the revision, the release, and the snapshot. Hashing the file is very easy. Hashing a directory is a little bit more complicated, but you can do it. You need a standard for doing that. And we add also some extra information that allows you to tell you this content in the graph. Where can I find it? Okay, where does it work? This provides you with full-fledged source code references, precise references for software all over the archive. It is part of the industry standard, which is a software package data exchange maintained by the Linux Foundation for the what are called software bill of materials. I don't know about these kind of things. It's traceability for industry. It is now an ISO standard. It took 4 years to get there, but it is an ISO standard 18670. Why do you need a standard? To make sure that everybody can build a tool that uses exactly the same format, that produces exactly the same hash. And the advantage of having this kind of thing is that, for example, you see this is exactly the reference to the fragment of the Apollo 11 source code we have shown on the slide number 1. So now, in the PDF slides, I can just include that reference. If I do this fires up my browser, if the connection is still there. You get exactly in front of the fragment of the code that you have been using in exactly the same contents. If you go up, you see the revision number, the place where we found this code, the last visit that we made to it for July 1st, etc. So this kind of thing. Again, nothing revolutionary, because if you are using platforms like GitHub or GitHub, etc., you can do the same. But since you are very smart people, I know, you immediately understood there is a fundamental difference. Actually, there are 2 fundamental differences. One, this is a link-in archive, not on a code hosting platform. So this means that if you come in 2 months, I hope you are not dead, I mean in 2 months, normally you find exactly the same thing. Second, the identifier does not depend on the code hosting platform. We compute this identifier for everything. Debian package, you compute this identifier. Python package, you compute this identifier. Something coming from submersion, the same identifier. So it doesn't matter. That's a big, big difference with respect to putting a pointer in a paper to something on GitHub. Now let me go back to this and take too much time. So we started this as an archive, but slowly over time we noticed we were building much more than a library of Alexandria for source code. By the way, this analogy with the library of Alexandria is very appropriate, because if you remember the myth of the story of the library of Alexandria, this is built during the Macedonian Empire. And so the emperor is sending people around the world to visit all different places and other libraries, finding something interesting, making a copy of what they find, and bring a copy back to this library, which was Alexandria. This is exactly what we do. Okay, so we go out, get copies of everything that exists, and bring in a single place. Now the analogy, I hope it stops there, because we also know that the library of Alexandria is very known to go up on fire. No? We try to take measures to avoid losing everything that we did, but we will go back to this later. Now it turns out that this is much more than an archive, and much more than a place where you put dusty all the source code. First, it is not just an archive, it is a graph, so you can track where things go on. Second, it is not any graph, it's a cryptographic graph, technically a Merkle graph. So this is basically a blockchain. Actually, it is really a blockchain. Because everybody talks about cryptocurrencies today, but cryptocurrencies are a blockchain plus a distributed consensus algorithm. Okay? Then you say blockchain and you forget that actually. Anyway, so for us it is really a blockchain. We do not need a distributed consensus algorithm for the moment. Then it is a place where people actually put software for reproducibility. And last but not least, if you have noticed, so we harvest code from 5,000 different platforms in tens and tens of different formats of version control system. We keep everything in a single unified graph that has a standard, very simple format. So basically we are doing for free, for you and for many other people, the data cleaning and normalization effort, which is the most annoying, time-consuming, non-interesting part of everything that people do when they do massive big data analysis or machine learning, etc. Okay? And you will see that many applications come from here. So application number one, if you look at the software for research, so what I showed before, okay, with these metrics we get in news research, everybody is using software everywhere. We would like these people to make the software available. Actually, in France, we have a policy that comes from the ministry, really top down. Unlike the US, France is really top down. So when the ministry of research says something, people have a tendency to actually listen and do it. And so the recommendation is to kind of open source software when you produce something coming from research. Unless you have a contract, unless there is something confidential. And how do you track this? You need to convince people to put software somewhere. And so here, you have tons of blue links to go over and check examples, but let me give you just a simple example here. For example, we are on GitHub. This is my GitHub page, and this is a simple library that I developed with a friend some 13 years ago. Okay? If you are curious, parallel map, this is a smart implementation of the map reduce protocol that uses OCaml as a programming language, and if you click on the Linux kernel to actually write this map reduce in a very simple way. This is a typical project on GitHub, okay? So you have a README, which is presented. And you see this little thing here, the green button there? This is a browser extension. If you install it on Firefox, Chrome, or Edge. Not Safari, unfortunately, for the moment, because I don't have an app. But if somebody wants to lend a hand, we can port it on also. This connects to the API on the archive to check what is the last time where it was archived. It connects to the API on GitHub asking what is the date of last modification, so it is being everything is there. Then I can click here and automatically go to the version which is archived in the archive there. If it was yellow or gray, you just click the archive is triggered immediately for you. Now, when we are here, as I told you before, everywhere you have this red tab that allows you to get the precise software cache identifier for what you are seeing. So if you are seeing a directory, that is a point to the directory. If you are seeing a bunch of lines of code, get a pointer to the lines of code. And the other thing which is interesting is now you also get a citation for software. You see this citation thingy? Because if you are working in programming languages, you would like to see your software cited, right? Not just a footnote, not just a paper that mentions the software. The real software, you would like to see it in the citation list to be recognized. But it was a mess, it was not standard on how to do this. But now you can get this kind of citation thing. It's actually a citation for what you see. This is a directory, but I can cite a quick snippet. And this comes because we now interpret this little metadata file, which is called meta.json, that contains your information on the software, etc., etc. If you don't like writing this with an editor, there is a generator for this kind of thing. And if you like to use what GitHub uses, which is citation.cff, we also support citation.cff, no problem. Okay. But again, the difference between having a citation on a code hosting platform and on the archive is you get the citation on everything. If you take code meta.json in a Debian package, in a Python package, etc., you get the citation for free. No problem, no dependency on the technology. Now to go back to the papers. Okay. This is a paper that actually we published with Elsevier, pardon me, but we published this in 2012. This was describing this library. So, typical, funny paper in this kind of work. You describe what you want to do, you want to implement a MapReduce, what does map do, what does reduce do, etc. And then we were so proud to be able to implement this in 29 lines of programming code. We were so happy. 29 lines MapReduce. Super cool. Okay. Well, on a multi-core machine, not on a cluster. Okay? And we tried to do our job properly. 2012, at the end of the paper, if you look, it is written here. The full source code of the library is available under OGPL license there, on Gitorius. Bad choice, but we didn't know. So, 2012. But we also put a copy in the Goldie installation system for coming libraries. Another bad choice, but we didn't know. So today, if you click here, we don't do it, we basically have nothing because the project has been bust. And if you look for the Goldie library system for Camel, it doesn't exist anymore because we wrote another one which is called Open, to which I actually contributed. So now you read the paper, you want to read the code, where is the code? It's there. But imagine that I write the same paper today.